And with no further ado, I'm going to turn it over to these gentlemen.
Hello, good afternoon. So this will be a hard talk to give because we just back from Black Hat where we gave the same talk. We had 50-minute slot, and now we have just 25 minutes. So I'll try to speak a bit faster, not too fast. We'll just remove a few slides, but hope it will be useful to you. So let's talk about testing crypto stuff. You know crypto better than the Black Hat people, so you need less introduction to this. When you want to test crypto, you test functionality. Does it work correctly? Does it work correctly on valid inputs? Do you get the right output? And when you send an invalid input, what do you get? Do you get some output that was computed in or do you get an exception or an error or something that tells the caller or the user that something's wrong? You also want to test the security of your software. So crypto software is software, so you want to test the usual stuff like memory corruption, normal logic bugs. You also want to test things that are more specific to crypto. You want to make sure that the cryptographic secrets, namely the keys, the plaintext, will not leak. Leak in several sense. It can leak in terms of if you get a memory dump. You can have also leakage in terms of side channel attacks. For example, in software, you have timing leaks, timing attacks. So you want to test all this with a single tool. And no such tool exists, so that's why we started this quite ambitious project. The things that exist today, you have, for example, static analyzers, things like the analyzers in Clang. They will tell you whether or not, they will tell you, well, how secure is your code, for example, in terms of memory corruption, in terms of undefined behavior, but it will tell you nothing, obviously, about the correctness of the crypto. If you implement RSA, it will tell you that your code is not buggy, but it won't check, obviously, that the RSA works correctly. It's the opposite for test vectors. So test vectors, usually it's a bunch of input-output values that you use to test that your implementation is doing what it's supposed to do. But it will not tell you anything about the security, the safety of your code. So you want to combine these two features. You have some more advanced tools to find bugs. You probably know things like AFL, which is kind of dumb fuzzer because it doesn't know what it's testing. It's trying to be as smart as possible to learn what inputs will maximize the code coverage, but it has to learn by itself. It's not designed, for example, to test, a PKCS11 parser. That's where you have things, for example, called smart fuzzers. In a smart fuzzer, it's dedicated to a specific crypto functionality. You might have a smart fuzzer for, elliptic curve Diffie-Hellman, and the fuzzer will try to send values that maximize the code coverage, like 10 different values that take 10 different code paths in order to test all this code. Okay. But it's pretty hard to design, and there's not many such tools available. There's a few commercial ones, but again, there's very specific. Maybe the most powerful solution is formal verification. So it's like getting a mathematical proof, a theorem saying, oh, your function, your library is correct and free of bugs. You have different types of verification, the one that will tell you that your code is equivalent to this code, and you have the other type, which is about proving security properties. For example, recently it was proved that the WireGuard VPN satisfied the forward security property just by looking at the WireGuard code. Okay. Now, what we want to do is to maximize the efficiency in terms of, like Pareto efficiency. You might be very powerful, like formal verification, but it takes a lot of effort. It's very expensive and it takes a few smart people to get it working. The test vectors, anyone can do it, but as I said, it's pretty dumb. It will have very small code coverage. So you want to be in the middle, maybe on the top of the green rectangle where we put the question mark. So our project was to create something that is between the dumb fuzzing, the dumb techniques, and the smartest ones. And that is as easy to run as possible. So I came up with this name, Differential Fuzzing, a year ago because it sounded cool. So yeah, fuzzing, but differential, It's actually pretty stupid. It's like just comparing two different implementations of the same stuff, but in a not so stupid way. It's been done before by a bunch of people. You have two examples there. More concretely, what we're going to do if you test a hash function or a PRNG, it's something that is deterministic. So same input twice, same output twice. So let's say you have two implementations, of SHA-3, of the SHA-3 function. You have the implementation P1, you have the implementation P2. So if the implementations are equivalent, for any input, you should get twice the same output. So that's basically what we're going to do. We're going to choose input values X, different values that maximize the code coverage, because we know that we're testing a hash function. So we know that we want to send values have different size or different alignments. And for each of these values, we'll make sure that P1 and P2 give us the same output. Slightly less trivial case is for public encryption. So in this case, the input generation will give you a message X, a public key, and the associated private key. The difference with the previous case is that here P1 and P2 don't do the same thing. They do the opposite functionality. P1 will be encrypting X, so you will get P1 of X, and P2 will be decrypting. So if everything goes well, after computing P2 on P1 of X, what will you get? X again. So if something wrong, if the two implementations are not interoperable, then P2 might reject some inputs, or P2 might compute any incorrect plain text. Okay, so now let's speak about our new tool.
All right, so we decided to actually implement that approach of testing. So we developed a tool called CDF, as in crypto differential fuzzing, which will basically do not only the functional tests GP just described, but also do more stuff. I'll come to that later. So CDF is coded in Go. No, it's not in Rust, it's not in C, it's in Go because, yeah, it was easy to code, easy to read, and it really is easy to support concurrent execution of the test at the same time. If you got 16 cores, why wouldn't you use the 16 at once? So, yeah. The CDF tool is actually made of 3 ports. So the executable, CDF itself, yeah, no, I'll come to that later. So, yeah, why would you use CDF? CDF will test the correctness, so the functionality of your implementation through differential fuzzing, but it will also test the security of the implementation against known edge cases, because CDF will be aware of the tested algorithm. So if you are testing ECDSA or RSA, it has special unit tests for those. So it's not just about dumb fuzzing, it's also about edge cases and strange behaviors, so we will check weak parameters and stuff like that. So CDF is really not about replacing formal verification, it's really about going further than just plain test vectors. So you heard about Witchproof, I guess. It's another project which is about unit testing. They've got really a nice set of unit tests. And it's a totally complementary approach. So we could reuse the unit tests in our tool to do the tests on both tested implementation, but they don't do anything differential. They are not about comparing implementation. They are really about testing just one. And they currently only support Java, which is not our case, but yeah. So how does it work? So you want to test ECDSA, you've got plenty of libraries implementing it, but they all got their very own API, so you are kind of, yeah, you got a problem there. So our approach is to design interfaces. So CDF will interact with your library through an interface program, which will translate your API into ours. So our API is pretty dumb. It's just plain command line arguments. So CDF can do a syscall on your proxy program and call your library afterwards. So for example, for ECDSA, you want to sign a message. So you will simply provide the public key coordinate X and Y, the private key coordinate D on the message, and then you get the output, which is R and S. So why do we need the public key too? Well, simply because of compatibility reasons with certain libraries. So yeah, that's really dumb. We plan to use AFL-like file-based interface later, but it's not the case yet. So the interfaces are really generic, and it's really meant to use everything in black box. So we won't be instrumenting anything. So you can bring us a script, C executable, anything you want, and we can test it directly if it's executable. So yeah. How does it work? CDF is made to actually use the proxy interface, which are in the middle there. So CDF will be calling the proxy interface, which in turn must be calling the libraries tested. So it's really dumb, but it works, and it's really, well, easy to code.
What I want to say here is again that CDF is the tough stuff we did.
Yeah, exactly.
The stuff at the bottom is what some people did,
yeah.
And in the middle is where you have to work. You have to write a
yeah, exactly.
few lines
so
of code.
If you want to test anything, you have to create the interface proxy programs in the middle.
It's pretty easy.
It's really easy to do. In Python, it's 35 lines of code to test cryptography.io. It's ECDSA implementation, so fairly quick. OpenSSL, you've got to clean the pointers. There is a bit more work, but still, it's not too much work. So GB will tell you about the tests.
Let's give you a few specific tests. We stick to very, very simple stuff again. So ACDSA, so elliptic curve signatures. Like I said before, the first program from, let's say, OpenSSL will issue signature, and the second one, let's say from, I don't know, cryptography.io, will verify the signature created by OpenSSL. So you can test a few things. You can test, for example, it's a good bullet point here because there's two kinds of ECDSA APIs. The one that receives a message, that hashes the message for you, and that signs the hash value. The other kind directly receives a hash and signs the hash directly. Now, what happens if you send a hash value that is bigger or shorter than the expected value? Some APIs, some libraries will complain, will tell you, oh, no, that's not the right size. Other ones will just silently ignore this and do whatever they can. So when you will send a longer hash or message, and they will just strip it till the size that they need. So they will ignore some bytes of the message to be signed. You also want to test the degenerate cases, the obvious invalid, not mathematically invalid, but insecure parameters. For example, if the public key is the point to infinity, so is 0 at 0? What if the private key is 0? What if you send a hash value equal to 0? So as you can guess, a lot of things can go wrong in this case. So some implementations reject these kind of parameters, but many accept them. Just to give you a short example, you don't have to look at the code, but that's an example of test that we do on ECDSA to check that it does not run into an infinite loop when you send certain kind of parameters. Now let's switch to encryption, RC encryption specifically. So like I mentioned, the first program will encrypt, the second one will decrypt. And you can test different things there again. You can test, for example, what kind of exponents are supported, what kind of modulus are supported. Let's look at like OpenSSL, for instance. So you know that a secure modulus size for RSA is 2048. But if you ask OpenSSL to use RSA with 33 bits, then it will accept it and generate 33-bit modulus for legacy reasons, apparently. In RSA, you use a public exponent, usually denoted E, and a private exponent to decrypt, usually denoted D. So D should be large, should be huge, should look like a random value. Now, what happens if you send a very small D or D equal to 1 or 0 or 2? That should not happen. So is your library testing this? The opposite, E should be small usually, but for some reason you might want to use a bigger E. Now, many implementations only allow you to use a small E. Sometimes it's fixed to 16,000, whatever. So that's kind of stuff that we're testing. And we also detect timing leaks, but we'll talk about this later. Or did we remove the slide?
No, we don't, yeah. So
okay.
Timing leaks, yeah.
Okay, we can detect timing leaks up to a nanosecond level, but sometimes what we find is that, oh yes, there's timing leak. But when we try to exploit it, it's impossible. The leak was too hard to detect, too hard to exploit. Okay, so that's...
Oh, we do?
Yeah, oh, we didn't remove the slide. Okay, so we did not reinvent the wheel. We took this nice statistical tool created by Oscar Reparan and other people. We just ported it from C to Go to integrate it into CDF. Okay, then what kind of stuff did we find?
All right, so we tried to test a lot of well-known libraries like GoCrypto, OpenSSL, MBTLS, CryptoPP. We tried it again for the DSA, ECDSA, and OAP, RSA OAP encryption. And what we found is that often they don't do everything as they should, or maybe they fall into some traps. Except it for CryptoPP, which was quite impressive, but is known to be quite paranoid about security, so it's a good thing that we couldn't find anything there.
I think they might wonder, why did we choose these 5 libraries and not other ones?
Yeah, so we choose them because it's well-known libraries which are basically secure and which are really studied by a lot of people.
We didn't go for the low-hanging fruits. We tried to like the most popular, the most critical piece of software. And these are maybe some of the most secure libraries you can find. Maybe you should in your PyCrypto because it's obsolete and not supported.
Yeah, and what we have written there is a number of issues. It's actually really issue. It's not security issues. It's more like small problems they could correct. So for example, for DSA, we found that many libraries were actually accepting invalid weak parameters, or even parameters which could lead to denial of services, which are quite bad, I mean. And other inputs could also lead to always valid signatures, which would discard the hash value of the message through a zero multiplication, for example. So it's really bad. The library should be issuing an error or something there. So if you look at the standard really is saying, okay, you should gain assurance of the domain parameter validity prior to signing. And when we checked if libraries were doing it, we found that most of them wouldn't. So for example, there, if you take the DSA signing process, you generate a random key, you compute the generator G to the k mod p mod q, and if that value is 0, then you just take another random key, and hopefully you shouldn't get 0 again. If you do, you're really unlucky on the third time. The probability of getting 0 again is so low that it's not possible. But some libraries are not checking whether G is 0 or not. But if G is 0, 0 to 2, 0 to whatever will give you a 0 value, and they are falling into infinite loops. So if the adversary is able to provide the domain parameters, which is a case which could supposedly happen according to the standard, then those are quite screwed. So yeah, this is what Go did when we reported the problem. They had a for loop doing the random key generation again and again and again at first. And when we reported it, they actually fixed it by limiting the number of atoms. So they are not checking the domain parameters. They are just checking they are not doing too many loops, because that's the probability of doing it is so low that it shouldn't happen. So GP.
I don't remember that we have removed so many slides.
Yeah.
We have 5 minutes.
Fine.
Okay, so maybe one comment, maybe you saw the table before, and when you look at this, so it looks like Go crypto really sucks because there's 4, 5, 6, 7 issues. But this should not be understood like this. We found some like non-compliance and some issues there, but Go crypto is really well written. It's really safe generally. It just means they're a bit maybe less conservative or less paranoid than other libraries. CryptoPP is really paranoid, and they try to do everything right. But maybe on other aspects, they're not as good as Go in terms of clarity, in terms of productivity. It's really easy to use the Go crypto. I encourage you to look at the code, for example, of OAP. It's really beautiful, and CryptoPP is usually a mess to use. So
yeah, it's template-based C++.
Yeah, don't tell to your friends, don't use Go crypto because and OpenSSL, it's OpenSSL. Okay. We had a conclusion at some point. Okay.
Yes, we do.
So if you're interested in this tool, there's still a lot to do. For example, we need some new interfaces. In other words, we need the ability to test more stuff. Like we don't even support Diffie-Hellman or CDH, which really sucks. So we want to add this. We want more tests. So if you look at Google's tool, they do many more tests than we do. So maybe we can try to find a way to include their tests into our software. We just tested a handful of libraries. Some of them maybe more secure ones. Maybe we want to use our tool on other libraries, which might not be as secure as this. And finally, we need to test our own software, which would be it's quite embarrassing, but we don't test our testing software very well. So we need to ask unit tests.
Yeah, we got like 40% of code coverage,
that's
which is bad.
Yeah. Okay, so thank you. We have time to take some questions. A small commercial plug. I've been writing a book with no starch. It's, you can order the early access version if you like. Okay. Thank you.
We have time for, there's like 4 minutes, so like 1 or 2 questions. Anybody?
Well, very specific question.
You again.
Okay. So as I told you at the other conference, this is great. I needed this yesterday. But now just playing with it, I've got a problem, really specific question no one else is interested in. The specification of the paths for the files on the command line argument, I'm getting no such file. And
yeah, but we just fixed this. I merged a PR 10 minutes ago before the talk. And so try again.
We had a problem because we changed the GitHub path, so the library in Go, they are bound to the GitHub
But if it still fails, post in the issue tracker and we'll fix it. Yeah. Thank you.
We have time.
I was just wondering, in your tables, there were a couple of NAs in your results, and I was just wondering what that was. Maybe I just missed it.
The library is just not implementing the algorithm, so we couldn't test it. I mean, if you don't have it.
Last question.
Thanks for your works. Have you tested PyCryptodome or not?
PyCrypto?
PyCryptodome, the maintained version of
PyCrypto.io? Yeah,
PyCryptodome.
Not this one.
I didn't knew it existed, so no, we didn't.
This is the official, not a fork of PyCrypto maintained and hardened. So I was really eager to see the result, but I know that PyCrypto is not maintained anymore. So it's not really.
I didn't know it existed.
Like maybe you could try it after.
Yeah, we could try it easily. I guess if it's the same API as PyCrypto, then
that's the point. It replaces the API.
We should test it.
We actually have a couple more minutes.
So yeah, just if you wonder, it's really easy to add new interfaces for other algorithms. It's really easy to add new examples. We are providing all the examples programs. So if you want to compare your own implementation, don't do it, of RSA OAP against OpenSSLs, then you can just take our OpenSSL example.
Or maybe at the previous conference, someone raised your difflung objection. He said, "Oh yeah, but we're not supposed to write our own crypto. We should use something which is available." So it makes total sense. But you might want to use our tool on libraries that you may want to use, maybe to compare their interoperability and just to understand how secure they are against our tests.
Yeah, and one of the big problems with crypto is that you get a lot of randomized stuff like ECDSA, RSA OAP, a lot of stuff is randomized, so you can just have test vectors for those. It's harder, so that's why you might want to use it too. Yeah?
Do you have plans to fork the common libraries like...
Hey, do you have plans to fork the OpenSSL or the main kind of popular libraries and remove all of the actual checks for generating stuff you're passing for verification? Because at the moment, if you're saying I'm going to generate something,
I'm not maintaining a fork of OpenSSL.
Yeah, I won't. No, it's not planned.
But we reported some stuff to OpenSSL, and from their point of view, it was not worth fixing because from the point of view, it's something a case that will not happen in practice.
Yeah, maybe I went too fast on that, but actually, when the standard is saying something, the libraries are not always really keen on implementing it because it has no practical incidents in their opinion. So if you don't come up with a pack, they will say, hey, if the attacker can provide the domain parameter, then he can provide the private key. Why would I care?
But often it's not exploitable until it becomes exploitable. So.
Yeah. Can I have a mic? Okay, I'm going to use. Can I have a big round of applause for these guys? They did a great job.
Thank you.